Hi, I'm Tyson, and today I'm going to show you how I use machine learning to predict equipment failures in cannabis manufacturing before they happen. I partnered with Decibel Cannabis Company here in Calgary to solve a real problem that costs them hundreds of thousands of dollars each year. Let me show you what I discovered. So here's the problem that Decibel was facing. Their manufacturing equipment breaks down unpredictably, and it occurs in about 32% of their production shifts. When this happens, the average downtime is 39 minutes, completely disrupting the production schedule. But the real cost comes from how these failures get handled. Emergency repairs cost 3 to 5 times more than planned maintenance. You have to rush order parts, pay technicians overtime, and scramble to fix things when production is completely stopped. When you add it all up, Decibel Cannabis was losing between $300,000 to $600,000 each year from unplanned equipment failure at their Calgary facility. So the question became, can we use machine learning to predict these failures before they happen? Can we give them advance warning so they can schedule their maintenance more proactively instead of reacting to emergencies? My research question was, which machine learning algorithm is most accurate for predicting these failures? I decided to test 3 different algorithms. First, random forest, an ensemble of decision trees, very robust, handles missing data very well, and it's also a strong baseline model. Second, XGBoost, or extreme gradient boosting. This is a high performance algorithm that's widely used in machine learning competitions because it's extremely accurate. And third, light GBM, or light gradient boosting machine. This one is optimized for speed and memory efficiency, and is very good for production environments. My hypothesis was that the gradient boosting methods in XGBoost and light GBM would outperform random forest because they use sequential error correction and to capture more complex patterns. Decibel gave me access to 9 months of real production data, 2,281 shifts total, spanning January through September 2025. From this raw data, I engineered 27 predictive features, including production volumes, quality metrics, downtime records, and maintenance logs. This wasn't simulated on public data. This was real proprietary manufacturing data from an actual company. I organized these 27 features into 5 categories. First, efficiency metrics. 5 features which include OEE, overall equipment effectiveness, availability rate, performance rate, quality rate, and downtime ratio. Second, temporal features. Things like day of the week, months, quarters, shift numbers, and days since the last maintenance event. This captures patterns like Mondays perform worse, or problems increase the longer it's been since maintenance. Third, lag features, what happened in previous shifts. So this includes previous shift downtime, OEE from the last couple shifts, and breakdown counts from recent shifts. Fourth, which was the most predictive, rolling averages. I calculate statistics over the last few shifts, like the rolling average of downtime, breakdowns, and OEE. This captured trends that show if the equipment is degrading or not. Finally, I created production metrics. 9 features which include units produced, planned production, breakdown counts, downtime minutes, and several others. The key insight here is that the equipment doesn't just break down randomly. It degrades gradually. The rolling averages let us see that degradation is happening. For my methodology, I used a proper temporal train test split. I trained on 80% of the data, which was about 1,800 shifts from January through July, and tested on the remaining 20%, 450 shifts from August and September. This is important because it prevents data leakage, and the model will never see future data during training. I trained each algorithm for 2 different tasks. First, classification. Will downtime occur this shift? Yes or no? I evaluated this using accuracy, precision, recall, and ROC-AUC. I prioritize high recall because in maintenance, missing a failure is far worse than a false alarm. I also use smote oversampling to handle the class imbalance since only 32% of shifts had downtime. And I used 5-fold cross-validation to make sure the results were robust. Second, I build them for regression. For shifts when downtime did happen, how long will it last? I measured this with mean absolute error, root mean squared error, and R squared. The goal here was to minimize the average prediction error so that Decibel can plan more accordingly. I was also very careful to prevent overfitting by using cross-validation, regularization, and proper train test splitting. Here are the classification results, and Light GBM was a clear winner here. Random Forest achieved a 90.3% accuracy with 94% recall. XGBoost got 87.1% accuracy and 88% recall, but Light GBM achieved 96.8% accuracy with perfect recall, and the highest ROC-AUC score of 0.95. That 100% recall is the most important number on this entire slide. It means that Light GBM correctly identified every single shift that experienced downtime in the test set. Not a single failure got missed. Looking at the ROC-AUC comparison chart, you can see that all three models performed well above the baseline, but Light GBM had a slight edge at 0.95. For a predictive maintenance system, this is the type of accuracy that you want. One false alarm could mean a technician does an unnecessary inspection, but missing a breakdown could mean hours of emergency downtime. So that means that perfect accuracy is ideal. Perfect recall is ideal. Now here's where things get really interesting and where my hypothesis was proven wrong. For regression, which is predicting how long the downtime would last, Random Forest won with a mean absolute error of only 7.8 minutes. XGBoost came in second at 9.1 minutes, and Light GBM was third at 10.3 minutes. Random Forest also had the best R squared of 0.71, meaning it explains 71% of the variance in downtime time. So why did Random Forest win? It's because Random Forest averages predictions across many different decision trees, which reduces the variance in continuous output. The gradient boosting methods, which I predicted would win, actually overfit slightly on this task. This taught me an important lesson. More complex algorithms aren't always better. Sometimes a simpler ensemble method generalizes better. Looking at future importance from the Light GBM classification model, the rolling 3-shift downtime averages absolutely dominated. It accounted for almost 64% of the model's predictive power. The rolling breakdown average was second at about 15%. This confirms what I suspected. Equipment degradation is gradual and predictable, not random. If the machine struggled over the last 3 shifts, it's very likely to struggle again. Recent shift history predicts future failures far better than any single metric. So what does this mean for Decibel? If they deploy this system, they could achieve a 30 to 50% reduction in unplanned downtime by replacing reactive emergency repairs with proactive scheduled maintenance. They could cut their maintenance costs in half because planned repairs cost 3 to 5 times less than emergency. Adding this up, they could recover between $150,000 to $300,000 per year. That's about 50% of their current annual losses from downtime. Now, evaluating my hypothesis, for classification, I was right. Light GBM, the gradient boosting method, won with 96.8% accuracy. But for regression, I was wrong. Random Forest beat the gradient boosting methods with a 7.8 minute mean absolute error. But that's actually great science. Finding out your hypothesis is partially wrong is just as valuable as proving it right, because you learn something new. In this case, I learned that simpler methods can outperform complex ones when you have limited data. Next steps would be expanding to a larger data set with multi-year data, integrating real-time Internet of Things sensor streams for live predictions, and actually deploying this at Decibel's facility to measure the real-world impact. Thank you. I'll be happy to answer any questions at the fair.